Good morning, everybody, and my name is Ingo Lütgebohle. I'm okay. Yeah, this microphone. Is this okay? Um, so I'm a computer scientist from the Computational Perception Lab at Bielefeld University, and I will be talking a little bit about visual surveillance, what we can do, and what is possible there, and what the limitations are. But first, let me start by giving you a brief overview of what visual motion analysis is about anyway. So the goal here is to get a compact description in a computerized way, symbolic way of motion. And you can do this at various levels, which are illustrated in the image to the right here. As you can see, the first level you can do motion analysis is at the body configuration level. If you look at these green cylinders here, they are intended to be about the body, the torso, the head, and the arm, and so on. And so the first way you can look at this is how is the body configured in a way. And if you look at this yellow trajectory here, that's also a way to describe motion. It's the motion path that the hand took. And last but not least, and probably the most familiar way to humans is this is an operation on the block. The block is the one he has here in his hand, and he operated on it in some way. And this is most natural to humans, but it's the most difficult way for a computer to do. So what can we use this for, actually? This is not just for surveillance, and actually, as I will mention later, I'm not a surveillance person. What I do is human-computer interaction stuff. So you talk with a computer, you make gestures to a computer, and it understands you. That's basically the idea. But another application is in games. Maybe some of you have seen this Sony iToy for the PlayStation 2, which has a camera, and you wave in front of it, and it can basically do the game interaction by just using your body instead of a joypad or something. One big area that has done a lot of the early work in visual motion analysis is motion capture for movies, where an actor plays out something and an interactive persona, a cartoon character or something like, is animated to do the same motion as a human, and you get very human-like behavior that way, much more human-like as if you would do the whole animation yourself. But the topic, what I will talk about today is a little bit touching on the topic of surveillance, because that's, of course, one area where motion analysis is probably not that well received. All right, a brief overview. First, I will give a more motivation and an overview. That's what I'm doing now, and talk about what we are doing, actually, so that you will understand the examples. Then I will shortly sketch why this whole problem is why this is a difficult problem, and what the surveillance settings are. Yeah, and afterwards go a little bit about analyzing and the analysis methods of locating humans in the first place, and then a method of tracking, which covers a whole number of methods for finding interesting points, looking what tracking gives us in kind of results, how we can analyze these results. And then shortly give a short introduction to some of the tools you can use for this, that you can play around with. And at the end, I will give some concluding remarks of what I think this whole technical review tells us about the possibilities of surveillance, what's possible and what's not, and what we can expect. Right, first, all my images in this talk will be from the human-computer interaction scenario that you see here, where we have a robot, actually several robots, and a human interacting with them. And this torso robot that you see here with the face and the grasp, and here it has a toy, and the human, that's one of our researchers, is showing in the toy. And this is just to give you an impression what we are doing with it, and why the examples always look kind of like playing with a child, because that's what they are. All right. Good. So why is this difficult first? We have several problems. The first problem is ambiguity. So if you just look at this one picture to the left here, it's difficult to tell what's going on. Is this person passing someone to the other person, or is he pushing it, what's going on here, actually? You can't really tell. And then you see the second problem is that of low resolution. As you can see, you can't see very much. But this is actually the typical resolution that you see on a TV when watching a football game. This is what humans get as input, and we do perfectly well on that. And this is because motion is such a big cue, but you have to make use of it. And the last problem that you will see very often is that of occlusion. Here you have two persons, actually a third one in the background, and they partly occlude each other. So you can only see one, here the one person you can see full, you can see his face, the other person is right next to it, you can only see half of his face and not much of his body, and this person is almost completely invisible. So these are some of the issues that we have to cope with. Right. And then there's one other problem that I like to call the roadrunner problem, which is also the motivation for this title of this talk. And as you can see, poor Wile E. Coyote here is a little bit too late, and the roadrunner is already gone. So what I'm trying to say here is that visual experience doesn't just consist of interpreting the action after it has happened. When humans interpret their visual surroundings, what we do is we have a visual input, a visual experience, then we know a lot about the world around us, and this allows us to predict an activity. And to predict an activity at a point in time when we still have sufficient time to actually act on our prediction and make something happen. And unless we teach that to computers, they will never be able to help us much, because they will only be able to analyze something that has already happened. And this is something that has not received very much attention in the computer science community, but it's a real problem for surveillance. All right, how do humans actually perform these tasks that I've been talking about? And as you can see here, this is a so-called point light display, and it's attached to the joints of a person, and so you cannot see the person or what the person is doing, but you can only see these lights. And for a human, it's pretty well possible to interpret what's going on here. And this is because we have an internal body model. We know how our body is configured and how we could arrange ourselves to look like this point light display. And if you see here, this is the original motion. So there's a person here, it's throwing a cricket bat or something. And if you look here at both of these in conjunction, you can see that the point light displays corresponds very well, and humans can interpret this. And why do we do that? Why are we able to do so? Because we have this body model. And one important insight from psychology here is that this body model is not just from looking at persons. We have this body model because we have a body that is just like the one we are observing. We know when we make a motion and we can see our arm in our visual field and we can walk around, and when we make certain motions we fall over, so they are not possible, and we cannot just like put our arm here and expect this to be a regular view that we typically see. So all this information, this experience we have ourselves constrains what is possible, and this constraint allows us to interpret what other humans do as accurately as we are able to. And this is something the computer can only look at a person. He cannot see, does not have his own body. He cannot have this motor experience. So if a computer has to be able to do the same kind of interpretation, this body model has to come from somewhere, and this is from humans. Humans have to specify this body model. So this is one very crucial point where the performance of a system is limited by human input. And this, just to give you an idea what kind of body models we are typically working with, it's a skeleton-based model. So you see arms, lower arms, upper arms, lower legs, upper legs, and you have the skeleton. What's the spine, right? And the sphere for the face, for the head. Right. Now let's talk a little bit about what surveillance methods are originally used for. Originally, all these methods for surveillance, they were developed for restricted areas. In restricted areas, you have a very simple problem. There's little activity. What little activity there is already suspicious. So if you can detect anything is going on, that's good enough already. And the use cases here are for alarming, and later on, if you know something has happened, then you can look at the video and tell what's going on. And so you have basically a few weeks that you need to store this stuff, because if you don't know that there was a break-in up to a few weeks, it's not going to be much use anyway. Whereas what we are most concerned about is surveillance of public areas. And in public areas, you have a much different, much harder problem, because there's always something going on. And so you first have to separate all these things into different persons, different activities, and then you have to classify them, tell them this person is just walking along or this person is hitting someone, and you to be able to focus on what is interesting, because most of what you see is not interesting. And what this usually suggested as a deterrent. There's nobody on site to be able to act, but like it's supposed to be this idea of when there's camera surveillance, you won't be doing any crimes because you're going to be caught. This is just a hypothesis, of course, and the hypothesis is based on the ability to investigate. So these surveillance systems are meant for later investigations, and of course, when something had happened, so for this use, you only need storage for a few days. Okay. Give you a little bit more idea of what the levels of analysis for surveillance are. So first you have a low resolution, low frame rate, long stretches of nothing going on. This is what makes surveillance the typical images. And what you do there is you categorize behavior, and you can do this at two major levels. The one major level is that you categorize regular versus irregular behavior. Regular behavior is defined as something that is usually going on in an area. So if you look at the entrance or so, it's typical that persons are going to be coming in. And of course, this is bound to the time. So they are typically going to show up between 8 in the morning and let's say 8 in the evening or something, depending on the time of building. And if someone's coming, doing something else there, maybe hanging around or so, that's irregular. Or if you're coming in another time, that's also irregular. And then again, we have a second level of description that is probably more typical of what humans do. This is a scene where first these two guys, and he's running at her, and then they're fighting, and last but not least, he's chasing her. So this might constitute a human level description. And this is basically what is most useful. And this, for a computer, the problem is that everything in the image looks the same. It's just a block of pixels, it's just numbers, everything is the same. So what visual motion analysis wants to do is teach a computer to detect the relevant parts of an image where something is going on and interpret it. And so first I'm going to touch a little bit on how the detection of relevant parts is going to happen, or is happening in systems, because as it turns out, this is a very difficult problem. And of course, everything else is based on the relevant parts. So if this selection is bad, everything else is not going to be very, very good. And I'm briefly going into ideas on interpretation at the end. Good. So the first approach is very direct. You just look for motion. Anything so take two images, compare them, and wherever they are different enough, there's motion going on, and look at that. And this example on the right is the output of such an algorithm, and as you can see, it's not very easy to interpret it, but it is possible. So there's two persons here. One, they are moving towards each other, and there's the hands of the person, here's the arm, and there's part of her face. It's not completely in the image. And you can see part of the body, but this is not very good. But this is a very easy method, and it gets rid of all the static parts in the image, but it doesn't tell you very much. And the one problem is that you have these holes where there's similar color. So visual input is not doesn't change from one image to the next, even though there's motion. And then, as you can probably imagine, if two things like this are overlapping, there's going to be an interpretation problem telling these two apart. And so first I'm going to talk a little bit about how you solve the problem with the hole, and then about the major parts, about the overlaps and the ambiguity there. Right, so this is one of those overlaps. So there's a person here and there's another person sitting in front, and well, this doesn't look very, very good. Okay. One approach is that you can look at the background. What's your background like? And everything else is interesting. So you take a reference image and then take an input image. And this is the result. So, and as you can see in this result, you have the opposite problem of the motion detection. There's too much in it. So here at the left, the door was closed in relation to the reference image. And here at the right, there's something, I don't really know where it's in here. And then the lamp is also, the lamp is light, and it's all based on intensity and color, and so the lamp is changing, and you have autofocus, auto camera calibration, and all this introduces changes that are not really what you want. And there's also, to explain this, the lamp just switched on. And so you see, because it's now lighter and more, you see I have all these areas around here where nothing actually is happening, but the way the algorithm works, it looks different, even though it isn't. So this is one problem that you get with the background subsection. And the lesson we should take from this is that it's quite difficult to determine what's actually interesting in an image. And one thing that you can learn from the store example is you have to continually update your notion of what's the background and what's the foreground. And of course you can tell if the same holds for a person, if the person would be sitting here for a while and not doing anything, afterwards it would be considered part of the background. So this is not as easy as it looks. Okay, but now for the ambiguities. Ambiguities are resolved over time. In an image like the one in the middle, you can't really tell whether this is one or two persons. It's just not possible. The input is not there. And but what you can do is, if you have a couple of images, so this is the first, then it's the second, this is the third, you can imagine this person is walking from left to right. And if you can identify this at the moment, and there's another person sitting here who's only moving his hands. And if you have this information over time, you can track this. And you track this, the person, by first computing a unique description. A description that is characteristic of this person in this scene only. And then you can refine in the subsequent frames of the image. And then you know that these two parts in the image, in the frames, are related. So first you have to have a similarity. And then, because similarity is not enough, there's lots of things that look the same. You usually also use proximity to an expected location. So if I know this person is moving from left to right, I expect in a subsequent frame, I expect it to be more on the right. And so this helps us too. First, similarity. One similarity is color, and there's this skin color idea. It might sound a little strange to you because skin color varies so much, but if you have a constraint like silhouette or something, or a motion field, then the skin color is actually pretty suggestive of human presence. And it has the added advantage that it focuses you on the parts of the humans that are interesting, which is the face and the hands. So as you can see here, this is our input image, and he's pointing at something. And this is the skin color filtered image down here. And in most parts it's empty, but the black parts are the ones that are relevant to us, and they are the skins. And you can see his face, his hand, and his other hand here down here. But of course there's also some garbage that is not actually skin, but looks the same. And so if we want to track skin, we have to do it by proximity. And well, proximity is not always a good cue. As you can see here, these two parts are very close to each other, but they are not the same face. So this is one of these problems again. Okay, so color isn't really cutting it. Let's look at a different problem. We can look for appearance. So one part of an image might be the face of a person. So an easy approach is to take this face, go to the next image, and look for something that looks exactly like the face, and like this face. The problem is there's always some little changes, and this method doesn't scale very much. You have to first, when you just look for what's this patch here, you have to first find this patch in the original image to have something to track. And so what's usually done here is an approach by Viola and Jones for face recognition. What you do is you combine a number of these small patches here, that's what they're called patches, and you overlay them on the image. And as you can see, this patch, for example, is pretty characteristic of the border between the eyes and the forehead. And this patch here is pretty characteristic of the nose. And if you combine those two, that could give you a cue that there's a face here. And in practical use, there's about 2,000 of these small patches combined. to pick out faces. And this general approach can be used for many other things. What it doesn't do is if I rotate my face, it looks quite different. And so this doesn't cope with that. And also it takes a while to acquire such a unique description. And one very promising approach based on the body model, as I outlined earlier, it's the same picture, is that you have an initial idea of where your body is. And then you just, disturbs this a little bit. Like, look, okay, what's going to happen if he moves his arm a little bit? What's going to happen if he moves his head a little bit? And so on and so on. And you can generate lots of hypotheses and estimate the possible ones. And that's where you can use your knowledge about the body, because some motions are possible and some others are not. And then you just, in the next frame, you look at the best match. And I have a video to show this. So this is the same guy again as my colleague. He's Purban. And so this is the original input image, and this is the body model. And here are some of the cues, and here's the skin color cue again, and here's an edge cue. And as you can see, there's, well, this is the cupboard, and it looks, well, that's pretty difficult. It would be pretty difficult to distinguish the two on their own, but using the body model, we can do it. And as you can see, these are on the right. The blue ones are all the possible hypotheses, and you can see it looks, if the arm has moved more upwards or more downwards, it's a possible move, but the best match is the one in the middle, the white one. This is basically the idea of body model tracking. And the trouble with body model tracking is you have to start somewhere, and also you need sufficient resolution, and as we have seen in the beginning, sufficient resolution is often something we don't have. Anyway, if we can take a couple of these methods together, and of course there are different methods targeted at different applications, and all this is a huge area. What do we get if it gets out? We get something like this. The first is a posture, so I segmented out a human from the image, and this is his posture. And then I do this over subsequent frames, and I get a number of postures that are associated with each other, and then I can try to infer behavior from these. And, well, I will come back to this example later on so you can try and guess what it is. One other more direct approach from tracking is that you use the center of mass position of the person. So for example, this person, it came in here from the door, up there, and center of mass moved down, then it moved here to the middle, stuck around a little while behind the person, and then went here and stopped basically. And you can try, and the trajectory is tried for interpretation, and this is actually one of the most common methods in surveillance at the moment. And the last one is a summary, where you overlay all these postures. And you do it in a way that the older ones are darker and the newer ones are lighter, and you get a very characteristic motion where it moves from dark to light, and I'm also going to come back to this later. One general problem, though, with all these results is if you assume tracking works, and it doesn't most of the time, but if it works, this is what we get. And this is not very good. I mean, what tells us what this is, right? There's nothing intrinsic in these examples that tells us what the person is doing. And also, in many cases, the appearance is the same, but the action is actually different. And so the only way here is to use examples for comparison. Examples that we know, where we know what's going on, and then compare our new input to these examples and to tell us what's happening. And to use this methods for machine learning, and there's also a talk about machine learning this evening, I think at 9 or something, and where you can get more details on these approaches. But I'm giving you the general outline here. General outline is pretty simple. What you do is you gather examples from training, and the human goes there and annotates these examples. Basically says, okay, this is a walk, or this is someone hitting someone, or this is hanging around, or whatever, and or walking straight, or something like. And then when you get new data, you compare it to your examples, where you know what the examples tell you, and you assign it to the category that is most likely from your example set. And There are a couple of problems, general problems with this approach, and first is that it's very example-based. You can only make a classification, which is this is called, for something that you have seen before. You cannot not categorize new behavior. And also the more general problem is that appearance is not equal function. Sometimes the same action looks very different from one person to the other. Sometimes you can have very different action look quite the same. And so this is tricky. And you also have a duration. An action can be like, I can walk slowly to the left, or I can like fast to the left, or something like that, or I can run, or I can walk. Sometimes there's a distinction, sometimes there's not. And in general, you can only resolve all these ambiguities when you have the context. And then there's the last problem, that we don't know at the outset what we are looking for. And what's the category? What is a good category to describe human motion? This is a more difficult problem than you might think, because we are so used to it, and we know our ways of categorizing human behavior make use of very much world knowledge. And this is not available to computers, so we need to find different categories. Okay, but first let's look at the posture again. And the idea here is that some postures are unique and they allow us to infer what's going on. And well, I would ask you, what do you think this guy is doing? Yeah, that's very good. Football is also very good. All these are possible interpretations. Actually is drunk. And so his walk is staggering around. But all these interpretations are actually possible, right? This may be the case. And for example, if I were on a football field, the football playing interpretation would be perfectly reasonable just from this data. Or the dancing interpretation, if I'm in a club. Actually, dancing and being drunk is kind of tricky to distinguish. But yeah, this is to drive home the point that the context is very important. And anyway, there's also a different problem with the posture approach, that is self-occlusion, where if I'm looking like this, I can't really, in the posture approach, you can't really see where my arms are. And yeah, this is just. So let's go to the motion history. And this is the one I told you about before. These parts are the ones that are earlier, and this is the later one. And this is inspired by human peripheral vision, where you know that the impression of that what's going on around us is actually not processed one frame at a time, but it gets blurred. And you can use such a motion history image also to compare to examples. You need fairly large motions for that. And it requires sufficient resolution so that the motion is large. And it's also very view angle specific. So for example, this is a guy sitting down. Well, you can see it. First he was here standing up, and then goes down a little bit and moves backwards, and this is the final position on the chair. And of course this would look very, very different if viewed from the front, right? And you wouldn't have this characteristic angle here that tells you that about the chair and so on. But if you have multiple views and so on, if you have lots of examples, then you can probably categorize something this way. And then the easiest part is trajectories, as about earlier. So this one is the same example as before, annotated with a couple of events. So first there's a person entering here. This is a start of our example. And then after 0.1 seconds, it's this position, and then it's holding here for 0.05 seconds. And then at the end, after 0.3 seconds, it stopped here. So this is a typical example of a trajectory description. We have the position of the center of mass typically. We have a velocity, how fast is the person moving, and this coincides with the duration, of course. And a big advantage of trajectories is that a low resolution is very okay. You don't need high resolution for that. But a disadvantage of trajectories is that there's not much information left. So if she moves her arm here, you wouldn't see that. Or if she's here, she's actually turning towards the person sitting here and putting her hands on his shoulders, and you don't see that in the trajectory either. But it's the most prevalent method because it works. So, and now let's look a little bit about at how we can actually recognize activities from that. So the one approach that's pretty easy is so-called event triples. And what you have is an event vocabulary. This is entering E, S for stopping, M for moving, and H for holding. And if you go back to this example, you have E moving, EH, E, M, H, M, S. S is this example. And then you take this in pairs, in threes, always three events one together, which is to give you a little bit of context. You have a current action, you have the action that went on before, and you have the event that happened afterwards. And then you just count and compare this to your examples. And you have the event categorization for your examples. And so where you typically have a certain sequence of events going on. So first I'm going to move a little bit, and then maybe I'm going to move my arms or something, and then I'm going to move a little bit back or so. This could be shaking hands. And of course, and the advantage of this is that you get a little bit you get more abstract. You're not so much on the appearance anymore. So this is really the only level that you can talk about activities going on because of that appearance versus function problem. There are lots of other methods, but this is one of the most simple. Okay, so let's summarize this. Tracking associates objects over time in various ways. It can fail relatively often. There are lots of edge cases. And even as we can see, there is not much hope there because even in humans, tracking fails quite often. If you see a person moving into a crowd and then he's moving out somewhere, we will have a hard time finding him. And there's a couple of robust approaches that have very little information, but work. And in general, with tracking, you still have no clear decision between relevant and irrelevant because your input is so ambiguous. All this results in a very hard problem for recognition. It has to be said that the state-of-the-art progress is very fast, and the robustness is something that is being worked on very much, and we will see all these algorithms work in more and more cases. But what we still don't see is this action interpretation problem that I touched upon in the previous slide, because all these sequences, these events, what constitutes an activity, what sequence of events constitutes an activity, that is still something that is given by humans. And well, if after 20 or 30 years of research into symbolic reasoning, we still have this part given by humans, you can really assume it's a hard problem. And there will not be an automated solution for the sequence learning. There are lots of ideas for this, but they also always involve lots of human input. So this is something that won't work. And give you a little bit of summary about the different stages. All these things I talked about are usually done in a processing chain. So first you have this surveillance camera here, and it's looking at the wall. And then the images are going to be digitized, and you have a couple. This is intended to be a sequence of frames. And first you have to locate your humans, segment them out so you get a body shape, then you track this body shape, and you get a path looking from above. You summarize this somehow, and then a classification comes out, and well, this is walking. And I only talked about the parts in the red box here. The classification part, as talked about, it's not about surveillance, but general machine learning is later in the evening, and a talk about camera technologies right after this one. So if you're interested in that, stick around. Right, couple of systems and implementations. One problem with implementations is that, of course, the implementations that are actually out in the open and getting used are not available to us. No surveillance company wants to look us at their code because it's, well, yeah. And so the only option we have is use research implementations or build our own. And well, I'm a researcher, so I use research implementations. And I have to tell you, the quality and the robustness, and especially the speed, they are not very good. And also because research applications, they have a very specific problem, and design an algorithm, and the software is really just there to show you that the algorithm works. and on this particular situation. And so many of the research applications are very specific with regards to their input, which also makes them difficult to integrate. But one nice library is the open source computer vision library, which is produced by Intel and has lots of contributions from researchers. And it has a very comprehensive algorithm support. So if you read about any algorithm and you don't have an implementation yet, but you want to check out if it works, go check out OpenCV, chances are it has it. And it's also pretty fast. You can read lots of video and all that formats. And it's written in C, has bindings for Python, so scripting language, people can check this out too. And it's available in Windows and Linux. The main drawback is it doesn't do anything by itself, it's just a library. But for your reference, there's a link here in the slides. And then there's the software application that we developed at our group, which is focused on integration. And it has only very basic algorithms and a plugin architecture. It's called Icewing. And has support for grabbing from Firewire, Video for Linux, and so on. And it has a very good support for plugin programming and communication between plugins. And these plugins can be written in C, C++, Python, MATLAB, a couple of others are forthcoming. And it doesn't run on Windows, it only runs on Linux, Unix, and Mac OS. But what you can see here is it's an example of this application. So this is the skin color detection, and this is the trajectory here on the right. And one of the things that makes Icewing interesting is that it allows you to set all the parameters for the algorithm interactively. So this is one of the parameter boxes down here for the two windows. And if I change something here, it immediately gets applied to the output window. So you can get a feel of how algorithms perform. And there's also, it's at SourceForge, you can download it. All right. So, to conclude, surveillance visual motion analysis has been developed for indoor presence detection only. And this is the only thing that really works. Everything else is edge cases. And the current methods are especially not robust for public areas. And when you want to get human-like results, you have to provide a lot of specific human input. And this is maybe something for the Big Brother crowd, who think that this might, give lots of information about what we are doing. Well, we only get lots of information about what a person is doing when you expend lots of effort at the moment. So this is not quite there yet. And especially the last problem, the Roadrunner problem, as I call it, the one that you really have to take a predictive stance, that you cannot only interpret, you have to make a prediction of what's going to happen, to act upon it. That's going to stick around for a while. So in summary, I wouldn't stake my life on it, and I wouldn't even pay for it. Right. Just a little bit of ideas where it's going. We are going to see more integration. All these approaches that I outlined, and there are lots of more, they're going to be integrated to make the systems more robust. And then there's this notion of the 30-pixel man, which is the low-resolution example from the beginning. There's lots of work on that, interpreting these kinds of resolution images. And one thing that, of course, we are also very interested in is interaction analysis. If you have two humans or a human and a robot telling what they do, it's actually can be easier to tell what a person is doing when you see who he's doing it to or who he's working with. And this is a research direction. And also one offer I wanted to make is for anyone who is interested in the details or wants to work on these technologies. And we could do a little bit of a workshop at the Congress here, if you want to. And if you're interested in that, just talk to me afterwards. So, with that, thank you for your attention. So, any questions? Yes. Could you take a mic, please?
Two questions. First of all, the skin color detection seems to have some racial implications that I was thinking about just now, especially if you start learning in an environment where you have groups of different race in different social classes. For instance, in an area where most of the crime or a lot of the crime is perpetrated by people of a different race than I was wondering how that works with the computer learning and sort of thinking about the racial implications a little bit.
Yeah, maybe just to that. That's a very correct question and very good question. And of course, my personal assumption is always that skin color detection was developed by white computer science people, like this, and because it's very easy. But actually, what you can do is you do online adaptation. So once you have a body model fitted to a person, you basically know where hands and face are, and you can use that to determine the color model of the person you're looking at from the image. That's a little bit more difficult, and it has the initialization problem, but it is possible. And this is one way that you can easily do black, Asian, whatever color you want. But it requires online adaptation.
And the other thing I was thinking about is if you're going to do learning, if you want to do have lots of behavior viewed from different angles with the description on it, you could look at a large collection of movies for which you have the script. Because even if you don't know who is David and who is Jack, you still have the words for the behavior with the actual image. But that's just because there's such a large collection of it.
Yeah, that's a very interesting idea, actually. Maybe someone from the surveillance community should check that out. But actually, for a human interaction studies that we are doing, this is what we are doing. So the example from before is from this experiment where we have a set script. We always know what the person is going to do, and the only thing that's changing is how fast they do it and in which ways. So that's the same idea.
Okay. I have a question about a question/comment about Effect TV. Do you know about that project?
No, actually I don't. What
okay, I'm not sure if they do any motion detection or if it is just a bitmap trick, but it has similarities. Some Japanese researchers using it for VJ performances and so on, but it's also on SourceForge.
What's it called again?
Effect TV, EFFECTV.
Okay, thanks.
SF.net.
Check that out.
Check it out.
One problem which comes to mind, and possibly is easier to solve than the behavior of humans, is the behavior of motor vehicles. And you could use this technology for, say, detecting congestion or collisions on roads and motorways. Do you know of any applications of machine vision in these fields?
Well, there's lots of it. And the whole tracking field was basically, well, tracking is from military tracking of targets. And that's where it originated. And then there's a whole huge field that is using this for traffic analysis. And actually the sequence example, the sequence learning, sequence interpretation example is from a traffic analysis application. But you have a much simpler problem in traffic analysis, because there's much less overlap and cars don't change shape. And not unless there's an accident, of course. So, actually, one of the problems of the field is that it has tried to take methods developed for this kind of problem and use it for tracking humans, and that didn't work so well. So what you are seeing currently is new methods being developed for these two different application areas. So there's still research going on in machine vision for traffic analysis for rigid objects, as you would say. And there's a different field that's trying to do this on humans. Does it answer your question?
Yes, thank you.
Right. Any more questions? Okay, so if anyone is interested, just talk to me. And so I can use the time for a little announcement. The one is that the hacking CCTV talk that's going to be right afterwards is definitely very interesting to anyone working in this field and or interested in camera technology. And there's also going to be a talk about video surveillance at German universities later in the day. Thank you again.